All right, so there will be 10 problems. I did it slowly. It took me about 1 hour, so there's not much time left for you to go to even think about. I don't know. So the most important thing is I also changed the problem a little bit. So I don't want you to always do the computation, too much computation, waste time. The key point is to set up integral correctly. Okay, that's the most important things. Don't focus on the answers, okay? It's easy to make a computation mistakes, but the most important thing is you have to show me you understand the problem and you know how to set up the integral, okay? This is the most important part. Okay, I still do a backward, because I think the more difficult problems at the end. Okay, so the first problem I want to discuss is problem number 10 from test 2 version number 2, the second sample test. Evaluate the integral by making appropriate change of the variables. So this is a double integral, right? And e to the x plus y dx, and where I is going to be given by this inequality. Okay. So first of all, you have to draw the graph. Absolute value x and absolute value y, okay, and less than equal to 1. So you needed to draw the graph. So the graph of the equation, this equation is going to be the square. Okay, so those lines has slope -1. So those lines has slope -1. So y plus x is going to be let's assume it's going to be u. Okay, then this line. Yeah, those lines, okay, has slope 1, okay? So it's going to be y minus x should be equal to v. Then you have to determine the value for the v. So which one gave the v? You know, I think clearly this v is going to be 1, and that v is going to be -1, because when v equals -1, that's a y intercept, right? Y equals x plus v. So v should be negative, and this line, and I think y equals, when x equals 0, y is 1, so y equals u equals 1. This line is u equals -1. So you clearly can tell the range of the u value for the line, like in that direction. Okay, so u is between -1 and +1. Then you can solve for x and y. Okay, you can solve for x and y. So this is where we can find a transformation. Now, if the parallelogram in different position, and then the equations for the two parallel lines will be different, okay? There are two pairs of parallel lines to form the parallelogram. And I will give you a little bit idea in general, okay? So let's work on this problem first. So clearly, here u is between -1 and +1. V is also between -1 and +1, okay? And when uv changes, you get all the points inside this region. Then from here, you add the two equations together. I think, yeah, subtraction. So x equals half of u minus v. Equation 1 minus equation 2, you get 2x on the left-hand side, and the u minus v then on the right-hand side divided by 2. So y equals, you add them together, okay? So just solve it. It's like solving the inverse function. All right, so now, so this map sends the square to that parallelogram. Actually, that is also square, but it's in different position. Okay. So now, next step, yeah, you have to write down. Yes, this is my D bar, right? R bar. Okay, let's use R. Okay, it's in the UV plane. Okay, so this is a okay. So this is the R. That's R. Okay. So now you have a map. Send the square in this position to that square. Yeah, if there's a deformation there. Okay. So this is the idea. So you can use this so-called substitution, two-dimensional substitution, to pull back the integral on R to R bar. So this is the double integral, right? And e to the x plus y dA, and becomes the double integral on bar, and the e to the, I still can use the x plus y, but later on you have to change the x plus y, and then the derivative of the Jacobi, okay, and dA. So dA by du dv, okay. And so you have to compute several things. What is x plus y? X plus y is already known. X plus y is just u, okay. And the partial as the derivative transformation, which is called Jacobi, the determinant. So you have to differentiate x with respect to u, it's 1/2. Differentiate y with respect to u is 1/2. Differentiate x with respect to v, and v. Okay. So the answer will be, the determinant will be quarter minus negative quarter is 1/2. Okay. So this is a 1/2. Okay, this is a determinant. Yeah. Now it's positive anyway. So it's absolute value still positive. And then you put into that integral e to the u and the 1/2 yeah, but this is over the rectangle, right, over that square. So it doesn't matter from which one first, right? This is e to the u 1/2. You can dv first, du first, doesn't matter. Let's du dv, okay? So that means you can evaluate the function with respect to u first. And this will be half e to the u still, negative positive 1, and dv, right? That is going to be e to the 1 minus e to the negative, and dv. This is a constant. Actually, this is a hyperbolic sine 1, right? So yeah, you can simply write as hyperbolic sine 1 dv, but this is a constant, and then take it out, you get 2y's of that. Okay? So this is a value. Now, of course, there's a possible to make a computation mistakes. So I don't focus on your answer. I look at the answer is wrong, and I look back. You have to show me the details, how to set up the integral like this. Okay, I want to make sure R bar is correct, and the Jacobi. This is very important. You have to list that. Okay, you just tell me you know how to solve the problem. You know the idea, main idea. That's, you get already 50% credits. Okay, so you have to learn how to express the ideas correctly. Okay, now how do we find the? Yeah, let me put a remark here. Suppose you have some parallelogram in the xy plane, right? How do you find the map? As if this is R, and how do you find the map from UV, right? A rectangle, this is R bar. How to find that? So the idea is you have to find the equations of this line, this type of lines, okay? So they have to fix the slope. So this type of line has a positive slope. So maybe this is y minus kx equals, y minus kx equals u, okay? Then you determine the value for this line, for these two lines. And then for those lines, and then it has negative slope. So maybe it's not necessarily the same k, so plus L, for example, x equals v. Then you determine the value for u and determine the value for v. Okay, and if this is a line, u equals u2, u1, and this is a that's u2, u equals u1. So you determine two values, and also for this one, for this line, v equals v2, and here v equals v1. So then when v changes from v1 to v2, you get all those pair lines between these two lines. Okay, so then here the domain R bar will be used between u1 and u2. V is between v1 and v2. So you get a rectangle. So this map you can solve. Yeah, you can and the y plus L x equals v. So what that tells you is you are getting a map from R to R bar, but then you can solve for x and y. You get a map from R bar, so R bar over to R. So yeah. So from here you can also get, you can solve it. U equals x equals So x equals blah blah blah, and the y equals, okay. So you can solve for x and y, then you get map from R bar to R. Okay. So this is a general idea, especially for the paragraph, how to find the pre-image of the paragraph from, the pre-image should be rectangle. Okay. So you make the domains in the standard form, then you can easily evaluate the double integral. Okay. So this is a general idea. And all right, so the next question I'm going to discuss is evaluate this triple integral at y squared, and the E is going to be the upper hemisphere. Okay, so E is the upper hemisphere. So how do you solve the problem? You really have to draw the picture first. Upper hemisphere, it's going to be like that. Okay. So when you look at it's up, the region is up hemisphere. So you automatically think about spherical coordinates. Okay. So spherical coordinates, you write down it's rho sine phi cosine theta, y rho sine phi sine theta, and z equals rho cosine phi. Cosine phi, what is a phi? That's a phi. Okay. Cosine phi is going to be the height of that point, right? And rho is the radius. Okay. And this will be the angle theta. So theta is clearly between 0 and 2 pi. Rho is between 0 and 3 because here's a 9. And the phi is clearly from 0 to 2 pi over 2, not 2 pi because that's hemisphere. When phi increase from 0 to pi over 2, and then you will see it's going from north pole to equator. Okay. So this is you get a rectangular box in the new coordinate system, rho, phi, and the theta. Okay. So actually, what you're doing here is still a three-dimensional transformation. Okay. So this is a rho. That's I don't know how to. Yeah, this is maybe phi. That's maybe theta. Then this is going to be a box. You know, it's going to be something like that. Okay. Okay, so it's a box. So this is this is going to be 3. Here's a pi over 2, and this is a 2 pi. So you have a map. This spherical coordinates actually gives a map send from here to here. Okay. So if this called E, then that will be E bar. So the idea is this triple integral y squared dv is going to be the triple integral of E bar. Okay. and this is still y squared, but don't forget there is a rho phi and theta. This is the derivative of this map, okay? And this will be v bar. Okay, so it's in the new system. So all the formula is similar. You see that if you have 3 variables, you can have a Jacobian 3 variable. But this one, you already proved that they already did the calculation is the phi and rho square and the sine phi. Okay, so you don't need to waste time to do that. In the book, it's already shown. All right, so the y square, what is y? Y is going to be rho square sine square phi, sine square theta, right? Sine square theta. Yeah, okay. So this is y square. And you have another, and then dv bar. Okay, now, so you can have a separate terms, okay? Because all those are not mixed up, but just all the functions of the product of those functions. So you can easily get rho is from 0 to 3, and one rho to the 4th power, 0, okay? And then another one is from 0 to pi over 2, and the sine to the 4th theta, okay? And the phi, okay, not phi, that's a phi, because sine square, no, that's cube, okay? Sine square and sine. And then here sine square theta is from 0 to 2 pi d theta. So my suggestion to you is stop here, move on to the next problem, leave space. Okay, you already gained almost all the points. And evaluating this integral, single integrals, it's bound to math 165. So you may run out of time. I don't want you to lose 10 points, 20 points at the end, okay, when I collect the exam. So you stop here. When you have a time, come back to evaluate. Okay, but before you evaluate, double check your work, the previous, is anything missing? Got it? Yeah. So you have to use the time wisely, okay? If you do, even you don't have a time to evaluate, you still get an A, honestly, because you only lose maybe 1 or 2 points at the end of this, if the rest of them is correct, okay? So don't just focus on the answers. You don't worry about the answers. Yeah. So I will stop here. I know I'm not going to evaluate the integrals. The first one is easy, right? The second one, you need the formula of this, okay? And the sine cube phi. Sine cube phi, the integral, you have to use a substitution because sine cube phi is going to be sine square phi and sine phi. And that will be 1 minus cosine square phi and sine phi. Then you have to use the substitution, u equals cosine phi or negative cosine phi, doesn't matter. Okay, so substitution. So that's my idea. So everybody knows if you get to that point, you know how to evaluate the integral. All right. Okay. The next one is also the triple integral. It's the same story for today's quiz also. And this is the triple integral and dv, and the E is a solid that lies between the cylinders x squared plus y squared equals 1, and x squared plus y squared equals 16. Okay, and then it is also above the xy plane and below the plane z equals y plus 4. Okay, so yeah, you still have to sketch the graph. So you have two cylinders, one is smaller and the other one is large. Right? Right? So the XY plane is here. The XY plane, yeah, so this is the XY plane. Okay? So it's above the XY plane. And below the plane z equals y plus 4. Z equals y plus 4. How do you draw the z equals y plus 4? In the YZ plane, in the YZ plane, when y equals 0, z equals 4. Okay, so it has positive slope. So this is a line like this. Right, when z equals, yeah, it's going to be like that. So there's a cut. Yeah, this is a, yeah. So I'm not sure. Make sure this is above. Yeah. So this is a, yeah, this is a will be the, so make sure it's always above the larger circle in the XY plane. Otherwise, you have a trouble. I think between them. I believe that this is a, yeah. So we are talking about this part. Okay. Yeah, this is a solid. Okay, double check. I think it touches. Yeah, it touches the larger circle at the point when y equals -4. When y equals -4, z is going to be 0, and this is also on the circle, right? So I think indeed there's a plane is above the xy plane, but it touches the circles. It touches the circle at that point, but that's okay. So now how do you solve this problem? You can use it's a cylinder, so it's automatically think about cylindrical coordinates system. Okay, and you can yeah, you can use a cylinder, but essentially you can also use the iterated integral. It's essentially the same. Okay, so cylindrical coordinate system, and remember x equals r cosine theta, right? Yeah, y equals r sine theta, and z equals z. Okay, it's actually this is a kind of polar coordinates in dimension 2. Okay, so now it clearly can say that spherical coordinates it is yeah. So if you use spherical coordinates, you can tell what is r, right? R is between 1 and 4, right? And the theta is between 0 and 2 pi because rotate. And the problem is for z, right? Z is between 0 and y plus z. Okay, z is between 0 and y plus 4. So y plus 4, y is going to be r sine theta. That's, it's not constant, right? So the domain, you know, actually what you're doing is this is z, this is r, this is theta. You're working in this coordinate system, okay? And then x, y, z, you know, you're given the 3 equations. It's kind of mapped from here to here. So, so the domain here, r is between 4 and I think this is a square. The only problem here is z, right? When theta equals 0, sine theta is 0. Okay, so it's yeah. I think this picture looks like that. When Yeah, it's harder to draw. Anyways, this is some surface above this domain. Okay, so if you want to change it to theta r, theta z, then let's call the this is a e. Let's call it e bar. Okay, so it's e bar is defined. E bar is defined by this coordinates. Okay, so the the triple integral becomes the triple integral on e bar, and it's x minus y still, but then don't forget this part, right? So actually, this is also the Jacobian in three-dimensional r, theta, z, and dv bar. But that one we already know that it is going to be just a row. It is just r. Okay, so you don't need to worry about. Yeah, this is because it's special map. It's already calculated. So now how can I iterate this triple integral? X minus y is going to be r cosine theta minus sine theta, and here's r and dv bar. Okay, then you still have to change it to the double integral or iterated integral, right? So you can say r is put aside. R is from 0 to no, from 1 to 4. Yeah, r is from 1 to 4. Yeah, let's go back to see. R is 1 to 4, and then theta from 0 to 2 pi. Then for each r and the theta, okay, and z is from 0 to r sine theta plus 4, and this will be r squared cosine theta minus sine theta and dz. Okay, since it's independent of z, so you will get just a product. Okay, so r sine theta plus 4, and here r squared cosine theta minus sine theta. Okay, and d theta dr. And I think I should evaluate r first, because this is going to be separate. You know, this is a product. No, it's not separate. Yeah, r cubed. Okay. Yeah, then you get sine theta, cosine theta. You can evaluate this integral. This is going to be, if you multiply this out, it's going to be r cubed sine theta plus 4r squared times cosine theta minus sine theta. And then if you can evaluate with respect to r. So the antiderivative will be, this will be a quarter of r to the fourth power sine theta plus 4 over 3 r cubed. So it's yeah. So you will get 4 to the fourth power minus, this is the sine theta, plus 4 to the fourth power minus 1. And this is the part cosine theta minus sine theta and d theta. Okay. Honestly, I think as a sine theta, cosine theta, if you multiply this out, evaluate, they're all going to be 0. Okay. The integral, yeah, think about what kind of products you are going to get, right? So when you multiply this out, sine theta, cosine theta, integral of sine theta, cosine theta, d theta is going to be 0. Okay, it's obvious why. Okay, and so the cosine theta times sine theta, the integral will be 0, and then integral of a cosine theta is also going to be 0 from 0 to 2 pi. So this 2 will be 0, and right, there's 2, and then integral of sine theta is also given 0. So only non-zero term is sine square theta. So this can be integral from 0 to 2 pi, and okay, negative sine square theta d theta. Okay, and sine square theta, you know that it's going to be 1 minus cosine 2 theta. So integral cosine 2 theta is going to be 0. So my answer will be 1/2 here, and I got 2 pi cancelled, and this will be this answer. Maybe okay, I have 99% this is correct answer. Okay, so I did skip a lot. You know, I only So when I multiply this out, I get 4 terms. But the other 3 terms, the integral will be 0. I even don't need to write down. I just needed to focus on sine square theta. So that saves you time. But as I said that, don't do the computation until you finish all the problems. Okay? But I carefully check the functions. I want to make sure computation is not that complicated. Okay, this is a problem just from the book. I just random pick up the problem. I like the format. Okay, so but the computation it takes a little bit more time than I expect. Okay, so the next one is also the triple integral. Okay, and this is going to be E is enclosed by the surface z equals x minus 1, z equals minus x squared, y equals 0, and y equals 2. All right. Can we draw this graph? Okay. All right. So this is a picture. And here's x, this is a y, this is z, and this x. So z equals x squared minus 1 is going to be x squared minus 1 when x equals 0 is it's negative 1. No, so this is a, So this is a parabola opens upward, and z equals 1 minus x squared is a parabola opens downward. Okay, this is in the xz plane. If no other restriction, you get cylinder type of a solid. Okay, and this is going to be like that. Okay, it's going to be like that. Okay, now y equals 0, y equals 2. So you got 2 cross section here. So this is a solid. It looks like 2 circles here, but it's not 2 circles. All right, so this is a picture. Yeah, this is a 2 picture. And okay, how do we solve this problem? Right, this is the E. Okay, and I would, yeah, it's not cylinder, right? So I call this one the domain D. Okay, so this is a D. So D is in the XZ plane. It goes like that. That's a D. Okay. So changes a triple integral to a double iterated integral. The first one is D. Right. For every point in the XZ plane inside the D, right? You use a line segment. Okay. So you fill this solid using those line segments. Okay. So Z is here's x minus y dz. right? No, sorry. So it's dy, so dy. Okay. So this y is between 0 and 2. Okay. Yeah, the idea is to project the solid onto a two-dimensional domain. Then for each point in two-dimensional domain, you draw the lines. So those lines occupy the whole solid, right? Then you can write down the iterated integral step by step. All right, so you evaluate this integral first. Yeah, dA is on the D, okay? So you get, for fixed x, the y is a variable, right? Y is a variable. So the antiderivative will be x times y, half of y squared. Okay, and dA. And that is going to be 2x minus 2 squared divided by 2 is just 2. Yeah, okay? So now we focus on this integral on the domain D. Then you still continue to change it to the iterated integral, okay? So this is a z and this is x-axis. Okay? How do you do that? You use a vertical line segment. Okay? So for every x should be from -1 to +1. So if for every x, the value those vertical line along this vertical line, z is going to be from the bottom part. I think that is x squared minus 1. The top part is going to be 1 minus x squared. It's from x squared minus 1 to 1 minus x squared. Okay. Yeah. Yeah, that's the range for the z. And then this is independent of z. So you take 2x minus 1 out, minus 2 out. And the difference of this one, 1 minus x squared minus x squared minus 1 is going to be also 2 minus 2x squared dx. So this becomes the integral of a polynomial. Okay, you can multiply this out, and you get it answer. Yeah. Right. Yeah, you can take a 4 out. It's going to be x minus 1, 1 minus x squared dx, and you have to multiply this out. Okay, in order to evaluate the integral. All right. So I do not want to complete this in single integral. Okay. All right. So this is the next one. Find the area of the surface that is a part of the surface x equals z equals x times y. It's lines between the cylinders within the cylinder. Okay. Find the surface area. Okay. Find the surface area. So it's surface area of the surface z equals xy, and inside the cylinder. Okay, so the cylinder, so that's x, that's y. So this is cylinder, right? Okay, the surface I don't need to draw it, just draw like that. Okay, it's just sketch the graph. Okay, so if this is a graph, it's defined. The function is defined as domain D in the xy plane. So this is the z equals f of xy, right? Step 1, write down the formula for the surface area. The surface area is going to be the double integral of d over d. It's going to be 1 plus fx squared, fy squared, and dx. Okay, so clearly you have to find the partial derivative of f with respect to x and then with respect to y. Okay, so you can, but you are while f is x times y. So fx is going to be y, fy is going to be x. Okay, when you differentiate with respect to x, you get y. When you differentiate with respect to y, you get x. So this is just x squared plus y squared and dx. And clearly you should use the polar coordinates to evaluate this integral. If you use the polar coordinates on d, this is r cosine theta, y equals r sine theta. Okay? And so the integral I is from 0 to 1, theta is from 0 to 2 pi, and this is 1 plus r squared and r, and d theta, d r. And the integral was, it's independent of theta, so it's 2 pi. And you can use substitution to evaluate this. Okay? Using substitution. So substitution is this. Okay. So you can evaluate this single integral. Yes.
Does it matter if you integrate with respect to r?
That's okay because that's the function is independent theta. You can switch the order. Yeah. To that point, I'll give you 80% of the credits. I just keep telling you that. Okay. So if you have time to come back to evaluate. So my suggestion to you is to make sure you finish 80% of all the problems, each individual problem. Don't just leave the last problem or 2 problems without even, maybe they're very easy problem, but you don't have time to do it. Okay. Find the mass and the center of the lamina. Okay, occupies the region, and you have the density function. So this is a D is bounded by curve. D is bounded by y equals 0, y equals 2x, x plus 2y equals 1. X plus 2y equals 1 is going to be the line like this. Y equals 0 is the x-axis. Y equals 2x is like that. So actually, this is going to be the region. Okay, that's going to be the region D. Right? Yeah. So this is y equals 2x, and this is x plus 2y equals 1. Right? And the density function low is going to be x. All right. For this problem, you needed to do lots of computation here, but on the problem on the test, it will be what? Yeah, the problem on the test will be much simpler. Okay. So for example, by the symmetry, maybe you can easily get the x bar. So first of all, you have to write down the formula. Okay. So A, the map, right, is going to be double integral of rho d A. Okay. Then the center of the mass is x bar, y bar. You have to write down what is x bar. X bar is the double integral of x with rho dA. Okay. And the y bar is going to be double integral x rho and y times rho and dA. Okay. the question is, how do you evaluate this integral? Yeah, I'm going to set up the integral. If you know how to evaluate the first integral, then you're okay. You know, this is a region, right? If you want to use a one single integral, you have to use a horizontal line, okay? But you have to find the y value. What is y value for this? The intersection part, let's check, okay? So y equals 2x, x plus 2y equals 1. Let's figure out the intersection. Okay, so x plus 2y is going to be 4x equals 1. So x equals 1 over 5. So y equals 2 over 5. So y is between 0 and 2 over 5. So the double integral can be changed to iterated integral. It's from 0 to 2 over 5, and then dy, right? Then the question is, what is x? X is, you have to solve for x, right? For the fixed y, x is going to be half of y here. X is going to be 1 minus 2y. So you begin with half of y, and because it's, you know, from the left to the right, then here's a minus 2y. Then this integral, the density function is x. So that's why you have dx. Okay? And then the antiderivative of x will be half of x squared. Okay. So finally, so you will get 1 minus 2y squared minus half of y squared dy. Okay, so you can evaluate this integral. Yeah, use one single integral. Evaluate this double integral, use one single integral. You don't need to define the function piecewise. Okay, so if you put dx inside. Right, and similarly for the x bar and the y bar, you know, because you multiply by x, that's the only difference. Right, and the other one is multiplied by y, so there's no big difference. You just need to evaluate these two integrals. Right, so the key part is this part. I want to see clearly. Right, how do you change the double integral? For this problem, I will look at whether you give me the formulas, the setting up, the three integrals, and then you have to show me how to change it to the iterated integral. What is the, you know, the best way to do is just use the one single integral, you know, because use the horizontal lines to fill the triangle. Yes.
Are we going to be like finding a centroid with spherical coordinates?
No.
Or the problem?
No. It's 2 dimensions. Okay. Only. Yeah. But the problem, if I'm not going to make changes last minute, is the problem on the test will be much easier than this computer. I carefully choose the functions. I don't want to waste too much time, like do the multiplication here. Look at this one. You know, about maybe 20 or 30% of students will make mistakes when they evaluate this single integral, because it's when you do the computation, you know, it's easy to forget the signs. It's not simple. Okay, so I carefully choose, and you also look at the symmetry of the domain. Sometimes it's obvious the x by 0 or y by 0. You don't need to know the center. Okay, because but be careful about the density also. Okay, now some for example in this case. Okay, so the domain looks like this. This is a domain, okay? But be careful. The density function is going to be y, right? Y bar. So it only changes vertically, right? But still symmetric with respect to about the y-axis. The density is still symmetric about the y-axis. So clearly for this problem, and here this y equal to x squared, and here this one y equals 1, clearly x bar must be 0 by the symmetry. Okay, you don't need to waste time to do that. It's obvious. Clear? Yeah, well, you look at the domain, look at the density. If I change the density function low to the x, then it's not, because you will see that from left to the right. No, cannot be x, because x will be negative, right? If I put the absolute value x, then the density function is still well defined. The density function must be positive, cannot have a negative mass. Okay, then yeah, then it's still, yeah, you can see that whether the whether it has a symmetry or not. Okay, so and then y should be somewhere, it's more heavier up, so somewhere here when you get the answer will be above the 1/2 clearly. So you choose a point, just need to calculate the y bar, but you still have to set up the integral for this. Right. Yeah, find the volume of the solid, right, which is below this cone and above this ring. Okay, this is x squared plus y squared less than equal 4, greater than 1. All right, so step 1, you have to draw the graph. I think the challenging part is to draw the graph quickly, 3D graph. X squared plus y squared between 1 and the positive 1 is going to be this ring. Okay, so this is a ring. Okay, and solid is below the this cone. The cone looks like that, but so in the space it looks like this. Okay, so that's my picture. So how do you do that? This is a domain D, right? The ring, the domain D. So the volume is just going to be the integral, the double integral of the graph, of the function for the graph. So this is a D, and this is going to be square root x squared plus y squared dx. This is just a volume is just the triple, it is triple integral of the constant one. Yeah, so that if the domain, if a region is this is R, this actually is a triple integral R, a constant function dv. But if you write down the iterated integral, you end up with this double integral. Okay, you can project the whole region into the two-dimensional domain D. Then iterated integral tells you that, and this is still 1, right? And dz is from 0 to square root x squared plus y squared and dA. So you end up with that double integral. Okay, so this is the integral of a constant 1 over any region in the space is going to be the volume of that region. Okay, so now you just use polar coordinates. X equal r cosine theta. y equals sine theta. Okay, I is between 1 and 2. Theta is between 0 and 2 pi. Then put into the double integral, and you can use any of them, right? It's going to be r and r dr d theta. And I is theta from 0 to 2 pi. I is from 0 to is from 1 to 2. Okay, that. Okay. Yeah, this r comes from square root of x squared plus y squared. This is from the Jacobian for the map. Okay. Yeah, this coming from the Jacobian. X and y and the theta. Okay. Yeah. This comes from square x squared plus y squared. Okay. So this is easy to calculate, right? First of all, you find antiderivative, evaluate at 2 endpoints, right? It's going to be 8 minus 1, 7, and this is a constant, so it's going to be 2 pi times 7, 14 pi over 6. Okay, that's easy. So I tried to put a problem like on the test. You can easily do the computation like this. This is an easy computation, I call it. Okay, you don't need a waste too much time. One more problem, then I'm done because I don't want to do the first two. Let's just iterate the integral. Sketch the region, change the order of the integration. Okay, so this is change the order of integration. Okay, so you already have the iterated integral, but you have to figure it out. You have to figure out the double integral because this comes from some double integrals. Okay, so the question is, what is this double integral? Then you change the order. Okay, so how do you do that? And you look at this, y is outside, right? That means y is between 0 and 2. 0 and 2. For every y, you draw a horizontal line. And x is between x for each y between 0 and 2, x is between 0 and 4 minus y. So x equals 4 minus y means how do you figure it out, right? Let's look at x equals 4 minus y. This is the line. Y equals 4 minus x. It is going to be negative. This is a line, right? Okay, so I believe this is a domain D. Okay, so this is a domain D. Okay. X is between, this equation is y equals 4 minus x. So it has negative slope, y-intercept is 4. And the x-intercept is, also, of course, it's going to be 4. So this is a 4. Here's a 4. Okay. So now you change the order, right? So when it's going to be 2, when here's 2, I think when x is 2, y is 2. Yeah. So you have to evaluate. It's good. First of all, you get it's between 0 and 4, right? And this is a dx, and the y is from 0 to some function. I don't know, right? The upper bound for the y variable depends on the choice of x. Okay, so if x is between 0 and 2, the y value is also between 0 and 2. But when x is between 2 and 4, the y value is going to be, you have to solve for x using the line. Okay, the y value is between 0 and 4 minus x. Okay, so there'll be some, you cannot, without the picture, you cannot get to that point. Okay. All right, that's it.